using dtrace. And this is one of many topics I can talk about, but this one's particularly interesting as we've been doing some new things recently. And I'll go through 3 visualization types fairly quickly, so you can get a sense of what can be done. The first one is heat maps, and a lot of you may have seen these by now. What I can explain here is the history of heat maps in a way that this audience would understand more than any other audience. It actually comes from PREX and TNF. And Richard McDougall wrote PREX and TNF, if you don't know about them, they were a predecessor to dtrace, and that was a static way of tracing about 24 system events. Richard McDougall created a visualization on top of it that showed disk offset. I rewrote that tool and called it dtrace TAS tool. And what you're looking at there is a heat map that shows where the offset of disk I/O over time on the x-axis, so that you can get a sense of the access pattern, a workload characterization. I created this tool, used it for a few things, basically forgot about it until later I joined Fishworks and worked with Brian on using dtrace to make a GUI. That was the Fishworks appliance. We started to care quite a lot about latency of events. The previous heat map I just showed you was disk offset, so that's what I would term a secondary metric compared to latency as the primary metric. Primary metrics are things that cause you to block things that are scaled, that are relative to your pain, whereas offset may or may not be. In terms of exposing latency, we were building filers, and filers are serving NFS requests or CIFS or other types. For each event, there is a start and end time and the latency associated with it. And so just to give you an idea of the data you have, that's a scatter plot. This is actually one I was using recently to work on a particular issue. This is dtrace based. I'm just taking the output of IOSnoop and then awking it into a GNU plot and then plotting it and coloring red for reads and blue for writes. You can actually see ZFS in the blues, ZFS flushing its transaction groups, which are really fast because it's going to a hardware cache. Scatter plots are great. The data is kind of there. They have a density limit. Things start to become paint. A problem with productizing this is that every single event has an X, Y coordinate. And if you start making filers that do 100,000 of these per second, it becomes difficult to process all of that data. So the scatterplot works, but it does have limitations. We, at the time, were very familiar with, and I'll bring it back up, it just decided to hide itself. We were very familiar with this type of expression, or this type of text-based visualization for understanding latency. I'm just going to make it fit. Let me clear the screen there, that's messed up. So just a dtrace one-liner that is doing a syscall write entry, and it's printing a histogram or distribution plot of write latency in terms of nanoseconds. That's interesting because we've quantized the data, and I believe the distribution was influenced by lockstat and the previous Solaris command. This works really well. Now I'm printing it out every single second. That has all the data, and I remember at the time I had a dinner with Jared, who's in the room somewhere, and Jared in particular I think was saying, we need to visualize this. This has all the data right there second by second. And the marriage of that and heat maps became the latency maps. So if you can imagine taking this, although not a quantized distribution, but a linear distribution using L-quantize, so that you're doing the aggregation of all those scatter point plots inside the kernel where it's cheap to do so, and then you're passing that L-quantize down to user land, and each of those outputs becomes one column in the heat map. And that was the most efficient way so that you could examine all the data and not be looking at just an average or just a maximum, or have the scatter plot problem where you have too much data. Here's one of the heat maps that I generated back on Fishworks Analytics, and I can't say I really expected to find things like this, but this lent justification to the desire to look at the entire distribution of latency. Just as a very quick introduction to latency heat maps, because they're an important type that we're using quite a lot now. The y-axis has latency, the x-axis has the passage of time, and if this was live, you'd see it ticking to the left. And each blocky pixel quantizes the number of events that were at that x and y latency range. So it's like a weather heat map where you're looking at clouds, and the darker it is, the more clouds or storm clouds there are. Here, the darker it is, the more events were at that latency, and the y-axis is just scrolled off, but that goes up to 8 milliseconds. For this particular workload, over time, we start off with what's a bimodal latency distribution. This kind of looks like a pterodactyl. And then there's the head, and the head gets a bit worse, and then it goes down into the neck. And then there's a wing of the pterodactyl. If we were just plotting a line graph, you can imagine compressing the entire y-axis down to a line, and so you would have lost a lot of these details, which are quite meaningful. Also, if you were to throw in a maximum, a standard deviation, a 99th percentile, you can throw in all of those numbers, but you're still throwing out the original distribution. And so we've found heat maps are very good at showing the original distribution, just like a scatter plot would, but in a more practical way that we can turn into products. And each time I see, now that we've done this, and we've actually found out that this happened to come from a test workload when I was looking at the throughput of disks. Now that we are using heat maps, I've found that bimodal and trimodal distributions are actually fairly common. You're looking at latency to a particular layer, and you have the fast events because you're hitting out of cache, and the slow events that are missing out of cache. Or the fast events for the fast path, and the slow events for the slow path. And so it is really important to look at the full distribution. Averaging that to a single line and throwing in those standard deviations and maximums and 99th percentiles assumes in case this isn't obvious, that assumes the normal or Gaussian distribution. And in reality, that often isn't the case. You have some complete other distribution. So now that we've done this so much, every time I see one of these line graph tools, I think, you're assuming that's a normal distribution, which it may be, but you don't actually know.
Talking about distributions, and life never resembles Gaussian. 15 years ago, Jeff Mogul, back then it was Deck World, came to the, at the time, stunning conclusion that Ethernet traffic was self-similar. You would take a glimpse at it, and it would have some bizarro fractal pattern, and you would shrink in on it, and it would be the same bizarro fractal pattern. Are you seeing something like, are you seeing self-similar sorts of distributions, or are you just seeing completely different other ones because it's disk and it just behaves differently?
Usually seeing other ones. If I zoom in, I'm not going to see another bimodal, or I could, actually to some degree I may, because within each portion of the beak, there may be the slightly faster code path and the slightly slower code path.
There's a pterodactyl in each beak.
There's a pterodactyl in each beak.
I just wondered if by getting new visualizations, you've been able to
That's the technical
discover,
term.
have you been able to discover new patterns of distributions for whatever you're measuring that completely buck conventional wisdom and may have some other precedent? The whole self-similar thing was stunning back in the day.
Yes, all the time, and it's in some ways it's surprising. In some ways, I guess it isn't, because if you invent a tool and you start shining light into somewhere that's dark that no one's seen before, oh my God, there's all sorts of interesting things in there. So not only that, the Icy Lake was one which I don't have up. There was another one where we wouldn't expect it to be this unusual. So you may have seen this before, but very quickly, the workload was a single-threaded synchronous write to a single JBOD of 22 striped disks. Very, very, very simple workload. It is a single thread. It is doing a synchronous write. There are 22 disks on the scene, but they're striped. And the latency heat map. Actually, that one has a positive bias. I think that's that one might be mirrored. There is another one that's very similar that has. This is either the mirrored or the RAID C, because if you have just right, the crosses pattern is uniform, but once you mirror and once you use RAID Z or RAID Z2, it has a more positive bias to the top because the operation is bounded by the slowest disk in the stripe. And so I'm able to look at one of these patterns and identify your RAID configuration. It's like, no, that one's not the stripe, that's something else. So yeah, patterns like this, totally unexpected, whoa, that's insane, all the time. It's because we're looking at data that people haven't looked at in that much detail before. So that's heat maps. There's an example of a heat map that's very famous. I'm sure many of you, how many have seen the YouTube video where I shout at disks? Okay. Yeah, most people. That's the heat map from it. I was actually demonstrating the latency heat map.
That heat map will be autographic copies of the intro book.
That's right, I should get the heat map printed out. We're actually now starting to use heat maps in other areas. I did a blog post recently where I used heat maps for device utilization. Didn't use dtrace, but I'll mention it actually works quite well. One I've done recently is using heat maps for sub-second offset. And that's where on the y-axis you have, on the x-axis you have the passage of time, on the y-axis you have within a second when did the event occur. And so this shows a React database where there's this hole in it where during these time offsets, there were no threads at all running. So the actual data that's being presented here is sampling at 99 Hertz.
This is dtrace-based.
This is dtrace-based, yes. The device utilization ones I skipped over were not. This is dtrace-based. We're using profile-99. I probably should do something a bit faster. And each time, in fact, you can imagine it paints these in vertical stripes as it's going along. And the number of threads that are on CPU denote the color. So darker means more threads. If it's completely white, it means there were no threads at that time. This is a production React database.
It should be insanely busy all the time, yeah.
It should be insanely busy all the time. And there was this hole carved out of it, which didn't make a lot of sense. And this happens to be from a joint cloud analytics tool. I was able to click on the white gap and it told me that was Zone ADMD was running. And the time that it was running and the start and end times were so similar to the gap that it really narrowed focus to maybe Zone ADMD, which is a single-threaded management daemon that's just managing memory across all the zones. Maybe that's somehow blocking the multi-threaded busy React database, which is written in Erlang. It didn't seem to make sense, but we had that focus that we really looked hard at it and found that was the case. We've since rolled the fix. It was because Zone ADMD scans memory to manage memory. It needs to understand the size. And it grabbed the address space lock. React was using Bitcast that does heaps of MM maps and M maps, and it immediately needed that address space lock, and so React blocked. Since React at that point was tens of gigabytes in size, it takes Zone ADMD a long time to scan its memory pages and then release that address space lock. So identified using sub-second offset heat maps. Another one, I've got all sorts of weird examples here. You can actually see what different applications look like across the whole cloud or on a single server. That's Java. And if you look closely, you can actually see this here is one thread that's waking up every second and sometimes doing a little bit of work. This more diagonal thread is waking up and probably doing more work each second, which is giving it a steeper slope. And this pattern here, I'm not sure what it is. It could actually be one thread that's waking up 20 or 50 times a second and doing some sort of other event. So there's 3 or 4 threads. Looks like there's another one just here. This is using sub-second offset visualization. If you're looking at this and thinking it's weird, yes, it's weird. I explained it in the blog post. A lot of people who saw this for the first time said it was very, very strange. But we are using it for characterizing workloads and identifying some issues. It happened to be remarkably simple to write in dtrace because all I need to do is take timestamp and then modulus with 1 second. So just chop off a second and then give you the remainder and then plot that. So one of the simplest dtrace enablings you can do is awk, bash, moonin.
Brendan, you're looking at CPU runtime here, right? Have you used that block I/O issuing?
Okay, so I should explain. Some of these early ones are the CPU runtime, so I'm sampling when something's on CPU. These ones down here are syscall based, so it's when it's doing system calls. Using that as a marker so that I can see the patterns. In terms of block duration, I don't have a block duration, but that would be an interesting one to try as well.
Or if you just plot like I/O issue time.
Yeah, you can see wild patterns.
Right. The I/O issue time, it is actually very similar to these guys because I'm doing the syscall. I'm doing all syscalls here. I just need to break it down into the I/O related syscalls. You definitely see the patterns for the I/O issue time as well. And this is another case, as Dan said, you create a new visualization and you discover all sorts of things that you didn't know was there, actually is there. The very last thing that I identified was this. This is where I have 2 threads bound to a CPU and they're running, and they're identical threads doing the same CPU work. What we expected to see was a simple checkerboard pattern as they took turns on the CPU. That's what we actually saw. Sub-second offsets, sampling what's on CPU. That's really sad, because if you look at a full column here, it's red the entire time. And that shouldn't happen. It means the kernel has let one thread stay on CPU for an entire second. So this really focused our attention on the scheduler, and that we may have been sitting on a scheduler bug. And it turns out we were. We've fixed that scheduler bug. Jerry Jelinek has fixed that scheduler bug. And I just posted this last night. This is what it looks like now. And so it looks much healthier. On each column, you are switching between those 2 threads that are running. And we don't have any of these cases where one thread gets blocked and is left in the dispatcher queue for too long.
So that was Linux?
This is actually SmartOS. So all the Illumos kernel.
And Brendan, are you going to talk about how we use this in production?
Sure, we're using all of these that I've been showing.
But in terms of the sub-second offset, I mean, considering we just nailed the customer problem with this yesterday, that we would not have, that we use a visualization that we would not have otherwise been able to do, I don't think, without this visualization.
Right, and that's what this one is about. This was an ingredient to another problem with a React database that a customer had, where the presence of another application caused the database to be off CPU for a long time. And when we're looking at it, the CPUs were not under a lot of load. And going through the mental mechanics of how everything works in the scheduler, it just didn't make sense that this database would be so adversely affected by the presence of another application. And it was really using sub-second offsets to
Do you happen to have those images? You've got those the images, I think, tell a million words, and I want to know if you've got those.
Oh, actually, yeah. I thought you meant that one. So that ingredient let us know that things could have been blocked for much longer than we expected. The other ingredient was actually seeing it, which I do have them lying around. And so when the issue was first...
No comment on who the customer is.
When the issue was first... I've talked to them before. They are actually cool about us mentioning it. When the issue was first shown to us, when Node was running along with React, this shows this is me capturing it live, working on the problem. In blue, I show Node. In yellow, I see React. You can't really see the yellow on the left-hand side of the screen. It's just inundated with blue. That kind of should be green if they were both running at the same time. This is actually a 4th dimensional heat map in that we're using hue so that we can click this left panel and highlight ingredients of the heat map, because the previous limitation with the previous heat map was you would see this interesting stuff, but that was it. You had to then go to the command line with dtrace to explain it, because there were no further breakdowns of that heat map. So we're now doing these 4th dimensional heat maps where we can use color hue to provide that breakdown. And again, this is all dtrace based. That unhighlighting node, that shows the React runtime on the left when node was present, and on the right when node was not present. And you can see how much node was being absolutely starved of the CPU. And this answered an immediate question. My first thought when the customer said, node is not coexisting with React very well, but the CPUs have a lot of idle time. I'm expecting there to be very short duration bursts, and our inability to identify this quickly, an artifact of us relying on 1 second measurements of tools, and I know this is something Theo can talk about. 1 second is starting to become way too long in terms of measurement tools. We start to need to see, actually, what happens on a 100 millisecond basis? What happens on a 10 millisecond basis? And that's what the sub-second heat maps do very well, because I was then able to click up the column and find out, is that the case? Are they not coexisting? Because for the first 100 milliseconds, there's a huge amount of work queuing, and for the next 900 milliseconds, everyone's idle. And by clicking up the heat map, I could see that was not the case. There was some other mysterious reason that React was getting blocked by the presence of node, even though there were CPUs idle all the time. So it was that heat map, and then we later, this is running with a fix. And so the presence of node without node, and so that's a very happy, there was a very happy screenshot when we took that in the last couple of days.
You described it, yeah, because the actual problem here is interesting in that the reason that we were starving, one was starving the other, is because React had outsmarted itself and was binding itself onto CPUs.
Oh.
So idle CPUs could not grab work, and then that was coming in confluence with the bug that Brendan mentioned, the scheduling bug. And you combine those two, and single React threads were being pinned for that, like that vertical red column. That would be pinning a single React thread. That would then pin all of React because it's multi-threaded.
Does this bug only affect it when you're bound to it?
Yeah, I mean, these are two bugs coming in confluence, right? And so these are, you need both bugs to, but in general, binding the CPUs is something you should only do cautiously, because you've got less information than the kernel does, even though sometimes you think you do it. And to be fair to everyone, like the documentation is very clear about, really you should only do this if this is the only thing running on the system. It's just not something that you think to check when you're...
So one of the things that where processors sometimes get bound up is when you interrupt threads. And I'm wondering, I'd love to get a little bit more detail on the root bug, because I'm wondering if this could explain some other behaviors.
This is FSS mostly.
Yeah, this is
FSS schedule.
But I would say you can use this visualization to go visualize some of the things you're describing. This technique is a really easy technique actually to go apply, go build a tool.
The stuff I'm looking at would be kernel threads. So
yeah.
Sure.
Yeah, this was a particularly interesting problem to work on, in that to get really good at performance, you need a very clear understanding of how the operating system works. And that wasn't enough. We had to actually measure how the operating system works and see it, because it wasn't working the way we understood it to work. This is why this visualization broke my head, because a thread should not have gone longer than its time quantum, but it was going longer than its time quantum.
So Brendan, one of the things we're interested in is we obviously use dtrace an awful lot for monitoring I/O,
Right.
And so have you. But we also seem to concentrate more towards the CPU utilization. Have you done much work on resource consumption and using the same sort of heat maps to visualize resources? I'm thinking in terms of things like memory allocation.
So yes, I did do a blog post on device utilization, which you may have seen. That's a, although I don't think any of this is dtrace based, but I'm using the same heat maps. Actually, this became an opus where I went through all the different techniques, including wireframes, that you can use, and ended up showing how a heat map could be used for device utilization, where utilization is on the y-axis. And you can then click on the top is devices at 100% utilization. It's great for the single device being pegged issue. So heat maps are actually quite useful here. I do really hope that these guys, these device utilization heat maps, get picked up by vendors like Microsoft or Apple and start to be used in standard performance tools when you have servers with far too many CPUs that make sense to do line graphs for. Because that one hurdle we have with adoption of this technology is that heat maps are kind of alien. And if this was a standard part of an observability tool by Microsoft or Apple, that might help us.
So one of the things I can imagine, oh, I'm sorry, could you?
Yeah, up here to something.
This is very interesting. It's very nice that you can have a physical representation of what's going on inside a computer. But is there a way you can write something that would look at your raw data and be able to say, this is the behavior you see, and you need to fix this now, and it would fix it.
So if I want to, you mean going straight from identifying the pattern to identifying the fix?
Yes.
They can be work done there. There could be ways as part of the GUIs to decorate heat maps with further information. So the simple one is if devices are maxed out, depending on the device, there's particular courses of action that you can take. But there may be some interesting work in what about other patterns that you see. So for example, the device utilization heat maps, and I think I had an example here. This shows the CPU utilization grouped around 50%, but it's not a narrow line. It means the CPUs have a wide distribution. And if that was disks, it's something that you want them to be more evenly, you want this to be a narrow line so that everything's running at the same rate. So that when one maxes out, they all max out at the same rate. And so I could imagine pattern identifying this and saying, that's not quite as balanced as it could be. You want your devices to be more balanced. And then there could be, you're right, right now I can picture drawing basically a pattern recognition chart and going through several different patterns for device utilization heat maps and the course of action. A line at the top means you have one device maxed out, a wide grouping means you have an unbalanced effect, and other things as well that I haven't seen yet. So I think some work can be done there. Okay, so I'll wrap up some other ones quickly, and then we'll. Yeah, it would be great to see these heat maps in other tools.
Like Navios, maybe?
Or Seconis? Where's the?
Well, I think that one of the keys is, I mean,
Oh.
the challenge with Nagios, less so with Circonus because of the room, that you need to have the instrumentation foundation that allows you to get that data, that distribution. And many extant or pre-dtrace tools lose that distribution.
But you also need context as well. Nagios doesn't have context. Circonus does, Nagios doesn't.
Yeah.
So you've lost context. You've already done, as Brendan said, you've thrown away your average data before you start. In which case you don't have the depth of context and information you go through that.
And Theo, I don't know if you want to speak about what Circonus is doing. I know this is yeah, exactly a top that you should plug in after.
I'll finish and then we'll plug in. But yeah, in terms of the heat maps, we're using them to narrow problems to a particular point, and then there is a point where you cross over and go to the command line and then finish the analysis. But it's not just the visualization that dtrace is particularly good at giving you the data. It's the scatter plot problem in that you can have a million events here and you want to aggregate them in the most efficient possible way. And we already have L-quantize, and Brian added LL-quantize for that. So there's many, and it's production safe. It's everything at once that makes it into a good foundation. So a couple of other visualizations very quickly. This one very quickly because a lot of people confuse this with dtrace and it's not. I was playing around with just PS minus EF and GraphViz and found ways I could plot the parent-child relationship processes. Everyone loved it and confused it with dtrace. It's not dtrace. That's an entire rack of systems. That's an entire data center or availability zone of systems. We're going to print this out large on the joint office so you can zoom in.
You can sell posters.
You sell posters, that's right.
To the people in this room.
The people in this room.
Or selling 80 posters.
I then animated them. This is still not dtrace. This is actually PS. This is still PS minus EF. I'm just taking snapshots every 1 minute. It kind of looks a bit creepy, like a beating heart. Those are HTTPDs, and the size reflects the CPU usage. Still not dtrace. This is like time-lapse photography because we're looking at it sped up. This is dtrace. So that's real time. That's showing. This is Nagios. Of course, I should recognize this by now. And it's On the left is taking snapshots every single second, like if you're running top or something like that. On the right, of course, is tracing every event. That type of visualization is dtrace-based because we're not missing anything.
That answers the darkest question.
That answers the darkest questions.
I have a visualization of something very similar I can send you on, which is we had a request a couple of years ago to actually visualize zone transitions within an installed ISP database.
Okay.
And what they wanted to do is visualize the creation and provisioning of zones, the transition through the life cycle of the zone. So it actually changed color and state. And we did like an FSM modification, actually sat there and cycled through like a PetriNet type model. So you actually see the zones come into being, you can see how they transition through their state in running, and then they shut themselves down as well. So the flying zones technology and so we do some sort of.
Well, I'll have to check that out. You can check out my blog post. I actually do that as technologies as well. There's a lot. This is the tip of the iceberg. There's a lot more I want to do in this space, but these are prototypes. The flame graphs were the last one I wanted to mention, and that is, if you've done something like this in dtrace a lot, where you're profiling stack traces, I do it all the time. Must do this every day for either the kernel or user land, where I'm sampling the stack backtrace at a particular rate. When you control C, you get a lot of data to look at. For this production MySQL database, that's the data. I actually created a website and was able to snapshot an image. The font is probably 0.0001 point, so you can't actually see it. But that really is the output of that dtrace command on a production MySQL database. This is rendered as what I call a flame graph, where I can mouse over elements. This is a SVG that does on-mouse event routines. And so that I can quickly navigate myself through the data and quantify. At the bottom, I've printed how many samples with that function that I'm looking at and what percentage of the total sample population. Because as a performance guide, one of the earliest things I need to know is, am I looking at the 5% problem or the 50% problem? With performance tools, you see problems all the time. You quickly need to quantify them and sort them and go and work on the worst ones first. And so this lets me do it by being able to navigate the sampled stack traces quickly and then get the percentages that I need. If I was able to eliminate this entire code path above it, I can eliminate 30% of the on-CPU time. So it's showing on-CPU time. The y-axis is the stack depth. Going upwards is deeper in the stack. The color is arbitrary, although we might come up with cleverer ways to the color is just random, so you can read it more easily. And then the width is the number of samples of that stack trace. The X to Y ordering is alphabetical. It has no meaning because we've sampled it. We don't know the relationship from one sample to the next. But we've been using that quite a lot to solve things.
And the generator for that is all open source. People can play around with that.
Yes, so I put that on GitHub, GitHub Gregg/FlameGraph, and it's a dtrace one-liner. So anytime you're sampling kernel stacks or user stacks, you can feed it, make the SVG, and go from there. Dave Pacheco added UStack support to Node.js, and that's where we're able to look at node stacks as well. And so lots of other cool things. Oh, there was a QEMU stack that I was that I was working on yesterday. I was printing these out and putting them on the office wall, and someone thought it was pretty. It's like, let's actually work. this is pain. I'm trying to solve a problem. I know it's pretty, but so those are three visualization types. We are doing some of these visualizations in Giant Cloud Analytics. Some of them I'm prototyping and I'm showing the code on GitHub. Visualizations are a great way to reach a bigger audience of dtrace. People see the pictures and they understand it more quickly than looking at the command line. I still intend to work on command line stuff as well. I'm doing this every day. But on the weekend I was trying to get unstuck with the dtrace toolkit. A lot of people have sent me, some people in this room may have sent me scripts over the past few years. And the big problem I had was I'm getting scripts from FreeBSD folk and I'm getting scripts from other operating systems, and I need a sensible way to support them all from one toolkit. So I think I've proposed a way that's going to work, and that will help get me unstuck so that I can keep developing that in the future. So thanks for listening. I'm sorry that went over time.